Okay. Um, the way that I was planning on running these sort of like focus sections is that it's much less about uh so like people can volunteer to talk, but it's much more focused on a discussion. So to that end, what we're going to do is I'm going to be a little bit ruthless about enforcing like 5 minutes. So at the beginning, we'll do a number of 5 minute flash talks. I'm going to be a little bit ruthless about enforcing the 5 minute limit. Um, there's I know at least two folks um, have signed up, but if there's something, if you want to do, if like on the fly, you want to do something, um, just like shoot me a DM. Um, because it's such a big room, I am like I much prefer to allow people to sort of just uh talk whatever they want. But because we're uh over 20 people, um, I think the thing that will work slightly better is if I moderate pretty heavily. So I will uh try to uh uh I will try to like aggressively interrupt on your behalf, so that we can try to have as freewheeling a conversation as possible. Um, so and sort of nominally the topic today is uh molecular machines with respect to materials. But as with any good discussion, uh, like let's try to keep it on topic. And so if you have something that's like like molecular machines or something that's like nothing to do with materials whatsoever, maybe hold it for another month. We're going to be doing these every month. But at the same time, like don't restrict yourself too much. So uh, that's uh, that's that. Does anybody have any questions before we get started? Okay, awesome. In that case, so right now we have three people who want to give 5 minute talks. There's Guillaume, Guillaume, if I'm pronouncing your name correctly, Tom, and Alexander have all volunteered. Um, So with that, I'm going to hand the mic over to Guillaume uh, because your name is first, and I'll let you take it away.
I can I share the screen or?
Let me advanced. Can I give you screen sharing power?
Probably easiest to make him a
security. Yeah. Okay. Don't abuse this.
Okay, seems to be working.
Yeah, and I encourage everybody to make liberal use of the chat room as well. So
It's not
cool.
wait, up. Up. It working? Yes. Okay. So just in 5 minutes, maybe I can present what I'm working on and related to the molecular machine and in the material field. So my name is Guillaume Vives. Guillaume is difficult to pronounce for English people. It's William in English, but that's the French version. And I'm working in Paris at the Parisien Institute of Molecular Chemistry. Here is a building of the campus, and we are located in the center of Paris. So you can see here the Eiffel Tower and the Pantheon, and this is the main tower of the campus. And I'm working in supramolecular chemistry, and I'm interested in cyclodextrin-rotaxane and polyrotaxane for imaging purposes, and also for making a molecular machine, so switches, and we are also trying to make some motors, exploiting the asymmetry of the cone-shaped nature of the cyclodextrin. And another topic I'm interested in, and I will talk a little bit more, is a switchable molecular tweezer. So it's a system that can open and close, controlled by a cation. So we are interested in this project to controlling properties at the molecular scale, such as optical, magnetic, redox, or even catalytic. And to do that, we want to use molecular motion of a machine. For example, of a system with two functional units here that can switch from a state where they are far away to a state where they are in close proximity. And this way we can opt to change their properties directly or via a small molecule. So you are well aware in this community that there are plenty examples of molecular machine from motors by Ben Feringa, nanocars from James Tour, and shutters, switches, and so on. But we were interested in switchable molecular tweezer, which are this kind of systems that can switch between an open state. So it's a system with a switchable part in red to a functional unit in blue. And by a stimulus, you can switch from an open conformation to a closed one. And if you have a real tweezer, you can expect to complex something. So this system is quite simple, but it's a mechanical molecular device that presents allosteric control and a double control, but via the switching part and the complexation state. Currently, we are interested in for the switching unit using metal coordination and using especially a therapeutic ligand that can switch between this W open shape conformation due to the repulsion between the nitrogen lone pairs and a U shape closed one upon metal coordination. So this is a switch. This is reversible. If you add a better ligand to remove the metal, the therapeutic will reopen. And for the functional part, we wanted something that is modular, and we decided to use metal silane complexes because depending on the cation here in the silane, we can have different properties. For example, luminescence with platinum or zinc, magnetic properties with copper 2, with manganese 3 or nickel 2, and even catalytic power. So we have designed a different system. First, we started with platinum system, and we have shown that we can switch from the open to closed one. And with the mercury, we have obtained an allosteric reconnection of mercury 2 with a system that can have a tweezer with 2 mercury, and the presence of the 2 mercury quench the emission of the platinum units. So the platinum silicon moieties are emissive, but when we have the system with 2 mercury, we have a quenching of the emission. So we have a kind of mercury sensor, and this system was selective for mercury 2 cations. Then we decided to look at controlling magnetic properties by mechanical motion. And for that, we use copper 2 in this system, which have shown that we can switch from an open conformation where the two spins located on the copper center are isolated. And when we close the tweezer with zinc, they become coupled antiferromanagnetically. And this is reversible. Again, when we remove the zinc, the system reopens. So we have a magnetic a control of the magnetic interaction by a mechanical motion. More recently, we were focused on multi-level switching, exploiting different orthogonal stimuli. So we use nickel moieties to have first 3 orthogonal stimulus. So first opening and closing the tweezer by coordination, decoordination, and then doing the same at the oxidized states that they generated 2 more states. And then we can add a third stimulus, which is gas binding. So we were able to obtain this 6-state switch. All of the states are stable, and we can switch from all of them by using the right combination of stimulus. So we have open and close at the neutral form, open and close at the oxidized form. Yeah.
I'm going to in fact be ruthless as promised. And so the thing that I will ask is like for the sake, like what is sort of like a point of discussion? What's like an open question that you would have for the group or people in sort of doing different, possibly complementary work for people to sort of like nosh on while we do the other two talks and possibly circle back on later in the
So
event.
I'm coming to it. I'm sorry, I'm a bit late. So just to finish, we also have shown some.
I'm being ruthless. You get to ask a question. What's the question?
So the question is, can we control use this mechanical motion to control macroscopic effect and have an effect on at the mesoscopic scale? So we are working now is this is just very preliminary results. So we are interested in controlling gels by this mechanical motion, and this is just a first example. We just decorated this tweezer with long chain, and as a preliminary result, we have shown that we can switch from a gel in one state to a solution in the other one, the closed one, and then switching back to a gel. So that's just an idea of, can we use this mechanical motion at a small molecule to change macroscopic properties, and for example, organogels.
So everybody think about where in your world that would really fit in. Cool. Okay, Tom, you're up next.
Maybe I can stop the sharing.
Yes, let's see. Let me, can you make me a co-host as well?
Yes, I can. Cool.
Great.
All right.
Okay. I have fewer options than usual right now. Let's try this. Can you see the big question on the screen or no?
I see a giant cursor.
Oh, that's weird. Okay. Let me, oh, here we go. Okay. How about now?
Yeah, now we can see a giant cursor. All right, cool. Take it away.
All right. Yeah. So, right. I'm going to start with my question. so as not to get, enforced against, but, yeah, the question is really sort of the main and obvious question when it comes to, approaching a molecular machines group for, a sort of materials focused set of talks. Right. And that is, of course, how we can, make transitions on the nanoscale useful on the macro scale. And so Guillaume just showed some work where the transitions that happen on the nanoscale happen sort of dynamically to switch properties, within a material that already kind of exists on the macro scale, right? Going from a liquid to a gel. I'm going to present kind of a different approach, and this is going to be less about my own actual work and more just about strategies in general. So pretty much the topic that I'm going to be talking about today, I actually spoke about in September in this group. So some of you may have seen some of this before, but basically my kind of answer to that sort of obvious prompt of how do we connect molecular machines with materials is via crystal growth control. So basically crystals, right, are a material that by their very nature propagate. Ordering is typically on a small scale, so nanoscale for ionic or molecular crystals. They're sort of more exotic and interesting. Well, not necessarily more interesting, but they're more. People are calling things crystals these days, but they didn't used to necessarily call crystals, such as colloidal crystals, opaline structures, and things like this, as well as liquid crystals, all of which have sort of orientational or positional order that is repeated in a periodic fashion. And so. I'm going to be focusing in this talk on sort of ionic and molecular crystals, but know that some of these concepts as well relate to kind of other forms of crystalline order as well. So crystals, by their very nature, propagate order by virtue of periodicity. So this is an example of a unit cell of potassium dihydrogen phosphate. It is 7 angstroms to a side. And this is a big crystal of that material that's been grown very, very carefully at the National Ignition Facility, or for use at the National Ignition Facility anyway, where it's sliced into slabs and then used for its nonlinear optical properties. So, you go from a unit cell the size of a cubic nanometer or so, even less really, to a macroscopic crystal the size of a person. So it's very clear that during the process of growing a material like this, there are many sort of opportunities for guiding and intervention. So the cover of this week's Science magazine is a great example of this, right? So this is a zoomed in view of a diamond type lattice that is on the micro scale within the skeleton of a starfish. So this is made of calcite, which is a form of calcium carbonate. And what's happened here is they've performed what's called an epitaxial overgrowth experiment on it, which basically means that they've dunked this lattice in a saturated solution of calcium carbonate so that it can sort of grow more crystals onto it. And what you can see is that this is a single crystal. This is a single crystalline diamond lattice structure. And so they've pitched this really as a dual scale lattice because they have the extreme scale lattice of calcium carbonate, and then kind of superimposed onto this, they have this lattice of on the micro scale. And it's a single crystal, and this kind of dual lattice structure gives it really interesting mechanical properties. And so it's known that so we don't know everything about how such crystals grow and how such structures form, but we do know that macromolecules are implicated. So here's an experiment where sea urchin spines are another example of a single crystalline sort of structure that is an interesting material with interesting mechanical properties on the macro scale. Basically, this is another single crystalline structure made of calcite, and it's been determined that there are macromolecules within this single crystalline structure that help shape it into the way that it is. So if you actually extract the macromolecules from the structure and grow single crystalline calcite in a petri dish, then you get sort of altered crystals that result from this. And so basically a way of altering materials using the properties of sort of molecular scale interactions is to sort of alter crystals as they grow, as happens in nature. Another example of sort of things on the nanoscale altering crystals on the macro scale are these sort of ice active proteins within nature. So there's ice nucleating agents and antifreeze proteins that both sort of are expressed in organisms, and we see in the ice nucleating, in both cases, we found commercial uses for these. In the ice nucleating case, we use it in artificial snow, and we use antifreeze proteins in non-fat ice creams to prevent freezer burn. I'm going to leave you just with a little picture of some work I published earlier this year. Basically, I've been interested in using polymers to control the sort of time course of growth of crystals in phase change materials, which crystallize rapidly and exothermically. This is a side-by-side video and sort of IR heat map of, this is 10 times speed, but basically of crystals growing in a patterned fashion as templated by a sort of polymer that's been synthesized using a photomasking approach. But yeah, basically my answer to this question involves sort of interactions during fabrication of crystalline materials. Yeah.
And I guess so one sort of prompt would be like, is there like an interface or another thing that someone in the group you would like really love to get their take on it, like from a different discipline or world?
Yeah, right. So I mean, I guess the open-ended question that I'd love people's kind of take on is so there's one direction of applying molecular machines to materials is having the molecular machines act sort of within a material, say. But another view on this is that as you are fabricating a material, for example, by growing a crystal, are there opportunities for interventions that molecular machines during fabrication or crystal growth or whatever can such that they can kind of guide the fabrication of materials, giving sort of opportunities for new fabrication modalities as opposed to their kind of use as actuators within a material that already exists.
Well, all right. Alexander, you are up. I think you should be able to just present because I made it so anybody can present.
Okay, yeah, looks like it's good. Can you see my screen?
Yes, we can see the PowerPoint window.
Is it in full screen now?
Yes.
Okay, great. Yeah, thanks, Guillaume and Tom for showing your stuff. So I'm actually going to show work from like grad students. So my name's Alex Lippert. I'm a professor at Southern Methodist University. do a lot of work in chemiluminescence switching for bioimaging. But this work is really the work of Uru Harris, who gave me permission to present her talk, where she's developed a way to do visible light micro patterning, which I think will have a lot of uses for people in this group. So I wanted to kind of get this out there and see what people think. And so I will try to skip slides and get this kind of quickly, given time. So basically what we've done is we developed a method to do microscopic patterning with light to do several different types of light-mediated chemistry. So we can do things like functionalize polymer beads, do light-mediated chemistry in single cells, actually make photograph quality printing. So this is on the microscopic level, and do microscale 3D printing. The system, kind of run down what we're doing is we're projecting a DLP projector through a microscope objective, so we can pattern light with around 500 nanometer precision. And this is an example of light on a target slide. We can use this for a couple of different chemistries. We can do thiol-ene chemistry. So we can have thiol modified beads, and then we have a dye with an alkene on it. This allows us to pattern on the beads, and then we can easily image it through with fluorescence microscopy. We get a resolution of about 8 micrometers, and we can do all kinds of things, text and yin yang designs, the beads. You can see the scale bar here. We can also use diazoketone Wolfram agent chemistry. And this is nice because you get like a fluorescence turn-on response, so the images are much more crisp and clear. Interestingly, we can use 2 different wavelengths. I like to do both of these chemistries. So we can, for example, do the diazoketone with vertical lines, and then the thiol-ene reaction with horizontal lines, and actually pattern them simultaneously and orthogonally. And we can do that with a couple different patterns. We could do this in cells, so we can pattern on cells. And this is with the diazoketone chemistry, and we can get down to single cell resolution. On PVA films, we can actually get photograph quality prints. And so this was actually work done by Josh, who kind of took a self-portrait of himself on a PVA film with 50 micron, 50 micron scale. The resolution here we get is about 2 micrometers with this chemistry. And then lastly, we can do photo curing, right? So we can pattern polymers. So kind of the last slide that Thomas showed me interesting. We don't have to use a mask. We can very quickly do patterns, very easy. We can do all kinds of patterns very quickly. And then we've also adapted it to do microscopic 3D printing. So that's kind of a rundown of what we've done so far. Going forward, we're working on applying it to things like self-propelled micromotors. Can we actually pattern molecular machines with some spatial resolution? We're making drug-loaded micro capsules, trying to turn this into a volumetric 3D enriching approach. Really, the long-term goal is to get this down, use super resolution techniques to get this down from like micrometers to the nanometer. And really the goal is to be able to pattern a single molecule at a time. And so thinking about the questions, one of the questions that keeps getting repeated is how can you take molecular machines and cause macro scale action? I think the answer to that is you have to put the machines together with kind of a top-down order or a bottom-up order, but some way have to order them on the nanoscale and the mesoscale and on the, up to the millimeter scale, whatever scale you want to cause motion on. And so kind of the question I want to leave with is how can we have this new tool now and we're trying to improve it, but we really like to collaborate and really like to kind of use it for different applications. And so kind of seeing some of the flash talks, I think there's some potential here. So be interested to kind of hear thoughts of others in the audience. And that's
Wow, that was awesome. That was under time. Impressive. Cool. So unless anybody else wants to say right now I'm ready to rock and roll and do another flash talk. Let's open it up to questions to any of the speakers about their talks. Just open questions to the group. Short thoughts. Yeah, that. This is really sort of very open, very freeform. Yeah. So just raise your hands, and I will try to route everybody correctly. Um, you use the reactions button at the bottom of the screen if you haven't done that before. And hopefully I'll be able to like see. Anybody? Thoughts? Oh, all right. Ted, go ahead.
Let's see. Can you hear me? Can you hear me?
Yes.
Yes. Okay. Yeah. I always need to check that. So one of the things I was interested about these three talks, I'm just wondering whether there are some experience you now have of designing larger structures with these different kind of molecular materials. So are there useful ways to create active molecular materials with desired material properties at a larger scale, say, continuum, kind of things like stiffness or density or attenuation or stickiness, and then vary them in controllable ways. So what I'm thinking of is you have these abilities now to make these molecular machines. Can we start thinking of how we would put them together and then view them as continuum devices or materials, but they would have very interesting, presumably actively controllable properties? Or are we still in the early stage of molecular materials where we can create things, but we can't yet do the inverse and say, I want this kind of material. What sort of machine would I use to get that? And if people have any thoughts on that.
I've got one. Basically, so we are able to do that in the field of, for example, polymers, right? Polymer material design has been quite well developed at this point. The question is, do molecular machines have something to add to that, right? Because you can vary your cross-linker concentration all day long to get things of variable stiffness, but does the ability to sort of in situ, do kind of real-time modifications add much to the science space?
Yeah, that's a really interesting open question, I think, of where these materials could be very helpful. If we can figure out how to make use of them.
Yeah. James, I think you have a separate thing.
Yeah, I mean, if the question is, how can you take a molecular machine effect that's at a small scale and affect some much larger structure? Rather than to build crystals, you can always destroy them. It's much easier to destroy things than it is to build things. So if you want to start, just break everything down. So we destroy cells with molecular machines. You destroy enough cells, you'll kill a very large organism. You want to have a crystal, you can break up the crystal with a molecular machine. So I think that if you wanted to start easy, sort of like a 2-year-old, just break things down. And that's much easier than building them up. That's just my thoughts on it. Thank you.
I actually have a question about that. Is there I completely agree with the statement. The question is there some kind of like critical path from getting very good at breaking things down to then be able to build things up, or are they just sort of like two sort of completely separate functions?
Well, I don't think they're totally separate. I mean, certainly a 2-year-old learns things by breaking things down. You can break things down selectively. I mean, how do adults break things down? They selectively put charges on the edges of a building and cause the building to collapse on itself rather than fall over and crush 20 other buildings in the process. So there are ways of destroying in that way. And what we do is we selectively kill certain cells with the hopes that then the organism can survive and rebuild itself where it was going to die otherwise. We kill the cancer cells so that the organism can survive. So there is a gradation of just destruction for the sake of destruction. Then there is controlled destruction. And then there is controlled destruction so that something else can take over and build. And then ultimately there's going to be bottom up building on the macro scale through this. So I look at it as more continuum.
Zach.
like your thoughts, James. To Tom's point, you can I could see how you could destroy certain sections of polymers, or you could embed nanoparticles to identify sections of polymer growth that should be eventually deleted. But in polymers, there seems to be a lot more flexibility for extending and or manufacturing things to a super molecular level. I'm most curious about how, in the realm of chemical catalytics and nanoparticle functionalization, what are the boundaries and constraints for control over how they develop into? I can see the pattern in polymer science and how that, Tom, you said it's very largely vetted nowadays. And there seems to be a clear path for how to build things up from there. But in the nanoscopic level, when you talk about, um, biochemical pumps, and things like that, how are they effectively controlled and constrained at a supramolecular level? I think that's a constraint. There seems to be different avenues you can approach this, and there's different constraints for each avenue. Uh, just thoughts I wanted to contribute.
Awesome. Anybody have a response to Zach's thoughts, or something, or if you want to go back to something that any of the speakers said? Yeah, Alexander, go ahead.
Yeah, I mean, my thinking on this is, if we really want to, I understand the concept of like breaking things down. I really like that. I think that's a good way to think about it. But ultimately, I think to be able to kind of apply molecular machines, we need to be able to do chemistry at a single molecule level, right? We need to be able to take a molecular machine, attach it where we want it, make components, be able to connect them, with that single molecule position. There's something that we can't do as, there's a lot of push for atomic precise package. Kind of in the standard, it's a little bit different. I think a single molecule might, in some ways, an easier goal. Have a molecule, like bond them together. Versus trying to get all the atoms together in the same place and bond them all the right way together. So I think that, before you can do some with supramolecular assembly, right? I think that's a role, but maybe combining like a supramolecular approach with a top-down approach to make the materials that you want. Thinking about something like a biochemical pump, right? If you have a protein and you have a pump that has a function, then you dissolve it in the membrane, it's going to go everywhere, right? You can like direct it where to go using a top-down approach. And this is something that, so I'll touch on kind of what we were going after. So that's just kind of my ideas, thoughts on where to go with that. So I'll see there's some other questions I'll pass along.
Zach, then Tom.
My curiosity with that is that at some point, when you develop things into bigger masses, bigger volumes, there's other chemical and just phenomena that forces that are pressing on the surrounding environments, and the environments are also pressing on those. So how do you sustain the inherent, back to Tad's kind of point that he brought up about the inherent properties, and how do you maintain consistency in those inherent properties such that they don't negatively impact or affect other surrounding systems and environments at a supramolecular level? That's my, yeah. Tom, go on.
Yeah, I'm glad you said this, because that relate to exactly what I was going to say, which is, so both you and Alex have talked about sort of confined processes, right? So like things driven by like molecular machines, action which is driven by chemical gradients, for example, or in the case of molecular pumps. In biology, right, we know that those pumps are always across a membrane, which has, a certain amount of impermeability and a certain amount of selectivity for the permeation of certain things. And so, am I right in identifying an area of potential need in this field as simply non-leaky containers on the micro and nano scale, so as to sort of be able to better define and program gradients and provide the thermodynamic driving forces for processes that we might be able to control? I mean, we've got, liposomes and polymersomes and polymeric materials for this, but like, maybe further developments might be welcome.
Alex, you have a response?
Yes, I think I've got a little bit to add on to that. It seems like this is going down a very biological route, which I don't know too much about, and I don't really want to know too much about. Biological molecules scare me. So what I was doing during my PhD was actually confining molecular motion to the solid state. So we were actually doing a similar thing with metal organic frameworks, and it was based on it's based on an old paper that Fraser wrote about this idea of robust dynamics. That if you're having something moving, you don't want it to be affected by anything around it. So you need to create the space to be able to do that. And one of the ways we were doing this was using metal organic frameworks that you can have these struts that are far apart from each other. So you can have one component moving in relation to another component moving, and they don't interact and they don't break each other down or prevent each other from moving. So there has been work in this field to overcome that. Now, how you do that biologically, I have no idea how that works. But yeah, there is. I just wanted to say there is work in this field for that of constrained molecular motion. I'm not going to say machine because that's a very, very specific part, and it's very difficult to achieve that. But motion has managed to be achieved.
Anybody else? I can throw out a thing that I was thinking that's like this is a more meta level thought, but it's like we use a lot of analogies when we're talking about this area, right? Because it's like we sort of have like it's very unintuitive what's going on at the nanoscale, and so we throw out analogies like destroying a building or milling things or what have you. And I guess it's like reasoning by analogy can be powerful, but it can also be really misleading. And so it's like, are there any heuristics for like basically saying like, when does a macro scale analogy hold and when doesn't it? That was just a thought I had.
That's a very interesting thought. I mean, throughout society, we often use analogies for a wide variety of things, and we wind up utilizing the same things in our new approaches that bothered us in previous approaches. And that's something I think we definitely want to avoid. Thanks for bringing that up. I think putting constraints on those analogies might be useful and could help guide a collective audience towards a potential common vision. But I don't know how they would describe where research needs to go.
I think the thing about analogies, like, and it's also a bigger problem here, is that it's just very hard to develop intuition about these systems. And like, it's like when I look at like two like macro scale Lego bricks, I can be like, oh, like those kind of like go together like this. It's very hard to eyeball all the different things that people are doing and figure out how they could go together. And so it's just like figuring out better ways, whether it's like better analogies or actual tools for developing those intuitions. It's an interesting thing. I'm mostly just talking to make noise and fill space. If anybody, Alex.
Yeah, so I saw Zach's comment earlier. I thought it was quite interesting, because we ran into this issue when we were actually trying to work out what was actually going on in the molecules that we made, and there is a dearth of analytical tools to actually work out molecular motion in the solid state and to work out what exactly is happening with what you're trying to create. So for us, we were making things moving in the solid state. Okay, great, perfect. So now you go, okay, well, what solid state tools can I go and use? Okay, crystallography. Let's go grow crystals and do crystallography of this. But then you run into the issue, okay, crystallography works because everything doesn't move. That's how you get diffraction patterns. And I'm trying to study something that is moving. So you get this kind of nice solid structure, but then the thing that's actually moving around, you just get a blur of electron density. It's very difficult to model. So then you go, okay, if I can't do crystallography, what do I do? Then we go to solid state NMR. So we label what's rotating, and then we get convalescence of the peaks depending on temperature. So temperature, they kind of blur into one, and then at low temperature, then you start separating these things out. So is there another way of working out something is moving in a solid state without using either of those two techniques? And as far as I could tell, the answer is no, we don't really have that. We've never figured out a way of looking at atoms um, in the way that the way that we want to look at them. Ideally, you want to take a video camera, right? You take a video camera, big enough lens, you zoom in and you can see the atoms moving around. But unfortunately, physics and nature doesn't really work that way. So I think we're at the limit of using nature at itself. We need to figure out some other way of doing it.
Alexander.
So I mean, the other half of my lab does a lot of bioimaging where we use optical labels. I guess for the mobs, maybe the side is what's kind of the weight scale of the motion. Is it not possible to think about like a resolution microscope or other optical techniques where you look at what motions?
We're talking nanoscale here. So the closest I've seen to anyone coming to, if you look at high resolution TEM, you won't be able to see the movement, but you can see like individual lattices. Trying to remember, there's a few people who have come out with papers recently about imaging solid state MOFs with this. But again, you run into the same problem. These things have to be done at high vacuum, extremely low temperatures to be able to see atoms. So to see motion at that level, you've already frozen it out to even be able to do the technique.
The super resolution microscopy can get down to maybe 20 nanometers. Maybe that's still like a little bit large of a length scale, but it's getting pushed lower and lower. And you don't have to have, high vacuum. This is in some ways compatible with live cells. It seems like it could be some.
We talk about light.
Yeah, optical. I mean,
your wavelength is just way too large to be able to see.
Right, but see,
things surely.
The super resolution techniques. I mean, if you have a single emitter, you can break that diffraction limit. This is
interesting.
I
didn't know about that.
Got Nobel Prize. So it seems like it would be something that would be potentially optical, but it sounds like maybe the distance regime is still a little bit large, and you would need a dye label on whatever you see is moving. But that's something that we're working towards to do in combination with the fabrication.
But how big is a dye label? I'm assuming that's a big molecule.
Yeah, these are probably about a nanometer big.
Right, so that we're talking about a ring, like a crown ether ring moving down a track.
Right, so I could imagine maybe like either making the dye part of the crown ether ring, or probably more likely just labeling the crown ether with the dye, and perhaps you could see it. But how big is how large the movement's just like nanometers, or is it tens of nanometers?
Yeah, just a few nanometers. There's a bunch of different examples. I think the longest one we've got is maybe 10 aromatic rings in a long line, and you get a ring to go across that track. I can't remember off the top of my head how many nanometers there are. I'd have to go back to the crystal structure.
Okay, yeah, so maybe, and it looks like that's would really be pushing the limits of the method. But there might be something there in the near future.
Zach, you've been waiting patiently.
I've been talking too. So, yeah, to further your point, that's where I was thinking, Alexander. Um, you know, leveraging some sort of tracer or some sort of iridescent nanoparticle where you could have it embedded in some sort of controlled environment or state such that it would refract the light in a mechanism or way in which you could measure it continuously over time and possibly adjust and implement some error correcting algorithms to mitigate any error in monitoring that light refraction from the tracers. So it's something of interest to me, and I'm very curious to see where that goes. But the question I wanted to pose to Alex J. Sturck's kind of point and furthering kind of our all collective discussion would be, if you had all the money in the world based off of what you know in your field and the theories and concepts that you understand, what would you be monitoring to iteratively improve your work in manufacturing supramolecular structures? So what are the things that you need to monitor, whether that's phenomena, forces, time, doesn't matter. What are those things that you think will be useful for monitoring to develop structured supramolecular machines and/or systems?
Hmm.
That's a very open-ended question to everyone.
Good question.
Yeah, I'm trying to think that because if you go with there's big work done in electron diffraction right now, but all that really does is just mean that you can use smaller crystals. You still get the same result as X-ray diffraction.
Steven,
So I'm not sure. I don't have the physics to know that.
Steven, are you there?
Yeah, let me, in, at one of the Foresight conferences, there was a competition, and on Sunday morning, I proposed a ion binding polymer that was in its thermodynamic state, a zigzag polymer, where mechanical force was the design concept for breaking up the ion binding sites at the hinge points of the polymer. And this is similar to what was mentioned in an earlier presentation. I can't remember who it was that actually did it, where we were, the subject was the terpyridine ligand, which had 3 aromatic nitrogens that would be either oriented towards a common ion binding site, or in its stretch condition would be orienting them outside of that focus point, where the idea is if this binding site, instead of using the energy of binding to the metal as a driver of the conformation change, that the mechanical stretching of it, if this group was repeated on a linear polymer, that stretching the polymer would cause it to, all these bonds to rotate out of orientation to then release the ion. You would, in a sense, have a metal sponge that could be used to demonstrate this as a functional capacity. You could potentially filter heavy metals, radioactives, things like that out of waste streams. So, for example, a copper mine might have a problem with downstream copper poisoning rivers and streams, and you could potentially build a site that would bind copper. The proposal that we made at the Foresight Institute conference was for binding heavy metals and cleaning up, ocean water and harvesting uranal ions for in a sense, mining uranium out of the ocean water. And that the idea of instead of using binding as an organizational feature, use it as a functional feature, and that would potentially produce a commercial product.
And I see monitoring of that being something that's quite possible.
Yes, I
Same.
mean, you can look at the absorption of specific ions as a sign of the polymer shifting back from a stretch configuration, which would be thermodynamically unfavorable to the organized crystalline zigzag structure, which would then be binding metal. So you could track it by crystal structure and you could track it by metal binding.
Yeah. Awesome.
Okay.
Yeah, just to comment on that, Jean-Marie Len made a small example of this idea with using a polyterpyridine ligand. And when he add lead into it, that's form an helicoidal structure. So it's the idea was done, but on small scale. So in this system, it was switching from elongated polymer to helicoidal coiled structure with ion binding, but on short scale.
Exactly. So it's basically the concept is looking at it as a monomer, whereas I'm suggesting it become a polymer.
Yeah. But it should be possible to do it on a larger scale.
So Isabella had a question. I'll just throw it out there. Is anyone thinking that a cryogenic trap might be useful for slowing down potential movements that are occurring? Possible applications might be in, any form of supramolecular structures, I guess. But cryogenic traps, is anyone heard of use of that? It's like a no.
All right.
Oh, wait, Alex.
Alex, yeah.
Yeah, I'm not quite sure what you mean by cryogenic trap. You mean for biological, so you freeze the sample?
Or you adjust the thermodynamic settings in which it's being monitored so that you slow down the overall
Right.
sort of entropic energy that it is forming.
Right, gotcha. Because we actually ran into this issue when we were studying some of our rotations and movements. Is that you get to the scale of the NMR time scale, so you have a motion limit which you can detect. So if it's moving too fast, you can't detect that, and also if it's moving too slow, if it's slow on the NMR time scale, you won't be able to see that as well. And when you're doing the crystallography, like a single crystal or a diffraction experiment, you're already doing that at cryogenic temperatures, so you can see things properly. So you've already frozen out the motion. So one of the ways we could actually help to prove motion was we would cool it down to low temperatures, and then you would see where your electron density actually is. So it's not just sat in one area, it's actually smeared across multiple areas. So that means it would have had to have moved forward and backwards. You freeze it all of a sudden and it gets locked in its lowest energy states, which could be degenerate.
Isabella, feel free to speak up, but I'll just bring up the thing that you're saying in the chat, which is the idea that you would lower the temperature 1 Kelvin at a time to like possibly find that sweet spot. That's the idea.
Yeah, so when we were doing the variable temperature solid state NMR, you can see that. That's exactly what we're doing, going down by different temperatures and seeing the difference at where your actual machine, in this case, it was labeled with deuterium. So we're doing deuterium NMR in the solid state on something that's moving. And you can see that there is a distinct temperature correlation.
So that there's almost an overlapping trend, I would say, between I guess biochemical related machines and polymeric related machines, and how you're monitoring them. I wonder if there's like a cohesive strategy for how you develop things at a nanoscale, and then is there a cohesive strategy for how you monitor its eventual polymeric elongation or cross-linking and so forth out from there. I mean, at what point does, NMR spectroscopy, TEM and stuff like that combined with, strength dial and materials testing? How do materials testing, or how does it relate to the testing done at a nanoscopic scale? And are there parallels that we can monitor and evaluate throughout the process of this manufacturing? Is what I'm wondering now.
Go for it, Thomas.
Yeah, so there are a couple techniques. The one I'm thinking of is nano indentation. That is sort of a mechanical sort of property testing scheme that does, is available on the nanoscale. Scanning probe techniques as well are generally pretty good at this because an AFM tip is small and can be used to do some sort of more spatially resolved and nanoscopically relevant mechanical testing techniques than sort of your standard like tensile tester. But when people are doing materials design, a lot of the time what they'll do is uh, either using simulations or simply trying to find correlation between some sort of measured nanoscopic property and a larger scale material property. Try to kind of tease out correlations. And that's how correlations get made mostly, right? Like, so
Yeah, exactly. And then furthermore, once you develop those insights about the material, those insights could be paired directly with biomolecular pumps or biomolecular machines in order to aid their self-replication. So the polymeric material could be literally a technology for aiding the monitoring and overall self-replication of biochemical machines. At least as I'm understanding it, it seems to be that there's more control over developing polymeric materials, and if you utilize the material and you can customize materials to a point where they're custom fit for particular polymers or ligands or capsids, whatever you want to call them, within a membrane, and you lay it out on that polymeric material. That polymeric material could be customized so that it aids the self-replication of those nanoscopic structures, I guess. And you've kind of demonstrated that in your research, Tom. And it seems that everyone else's research is all very methodical, controlled at a nanoscopic level. And if the properties of those processes were evaluated further, you could correlate how they behave in larger aqueous bodies or systems to be paired with a certain polymeric material that could effectively aid their development. I mean, Tom, do you see that as like a potential avenue where research collaboration might go?
potentially, I mean, it depends on the goal, right? So yeah, you've been talking about sort of your thinking and work involving kind of self-replicating materials, right? And that uh, the types of kind of testing that you do toward that avenue would be different from the types of testing and correlation drawing that you do if you were simply trying to like make a material that has properties that have been tuned to a specific like um, say tensile strength in a given material of a different given type. But yeah, no, I think getting together people who are sort of good at molecular scale material design and good at larger scale like property evaluation is a good and fruitful direction for collaboration, probably.
So, and on that note, I do need to go run and catch a flight. I'm gonna close the room. I really like if you want to keep talking. Like, I really encourage you to like keep talking about these things. Continue the discussion. Either email. There's the Discord, and we will see you next month. Really appreciate the discussion, everybody.